rational functions, things that are rational functions, are just polynomial over polynomial. So you've got some polynomial function on the top over some polynomial function on the bottom. It turns into just a big fraction. Everybody's favorite part of math, fractions. We love them so much that we hate them. Okay, so fractions with polynomials is what we're dealing with here. So big glaring thing that happens with every type of function we've talked about from chapter 3 all the way through is the domain. And there's a major red flag that exists on every problem for these two sections. There's a polynomial in the denominator, then there's the red flag of x's in the denominator. So we've got to take care of that. That's happening on every problem. So domain, again, set that denominator equal to 0. And then solve. Okay, so that's the first thing that you would do. Before you do anything else, get the domain of the polynomial or the rational function. So set that polynomial that's in the denominator equal to 0, solve it. The method that you want to try to use to solve that, in most cases, is going to be factoring. The reason that I know if it's a quadratic, we know we've got all these other options as far as solving it goes. We can solve by square roots. We can solve by quadratic formula. That's possible, and that will get you the domain. But the factoring is going to be handy because the next step is to try to simplify the rational function. Okay, so simplifying. We're going to cancel matching factors. Hang on just a second, guys. Got a visitor here. All right, guys, here we go. So simplifying is the second step that you're going to do, and to do that, you're going to cancel matching factors. Thus, going back to the domain, solving by factoring, you also are going to want to factor the numerator so that you can find matching factors to cancel out. That doesn't mean you'll always have stuff canceling out. It just means that you could have things canceling out to simplify that fraction. So we want to try to get that fraction in simplest form. Once you've got the fraction in simplest form, the next thing is to look for these things called asymptotes. Asymptotes are these imaginary boundaries that shape the graph. Okay, you can have vertical asymptotes, you can have horizontal asymptotes, or what we call oblique asymptotes, which are slanted out of that. And there are certain rules for finding those things. The easiest ones to find are the vertical asymptotes, so we always start with those. Vertical asymptotes are taking the simplified denominator and set it equal to 0. So set the denominator of the simplified fraction equal to 0. So it's got to be the simplified fraction. So your domain, if nothing cancels out, your domain, what x cannot be, are the same things as what your vertical asymptotes are going to be. If you have something cancel out, you may have only part of your x restrictions as your vertical asymptotes. So the numbers that you see in the vertical asymptotes and the numbers that you see in domain should always kind of match up. Okay. Your vertical asymptotes, though, you can have some of them, they will have the same or less number of restrictions on x as the domain goes from there. So vertical asymptotes are the first thing that you would want to find because it's the easiest thing to do. The next one is the horizontal asymptotes and obliques. So let's talk about horizontal asymptotes. Horizontal asymptotes are they exist at different ones exist based on the degree of the numerator compared to the degree of the denominator. So there are a couple of rules that we need to look at for that. The first rule is if the degree of the numerator is less than the degree of the denominator. Okay, so that example of that would be something like this: x squared plus 9x minus 3 over x cubed plus 1. There's an example of one where the degree of the numerator is less than the degree of the denominator. So top has the highest exponent of 2, bottom has the highest exponent of 3. If that's something that's going on there, if it's x squared over x cubed, or maybe it's x over x squared, or x to the 4th over x to the 6th, something like that, the top is smaller than the bottom, then your horizontal asymptote and we'll abbreviate that from here on out as HA, is y equals 0. Okay. The degree of the numerator is less than the degree of the denominator. Your horizontal asymptote is at y equals 0 automatically. Okay. So y equals a horizontal line, it's a dotted horizontal line when we draw the graph, at y equals 0. That only happens if the numerator has a degree that's less than the denominator. That's when that happens, okay? Another scenario that gives us a horizontal asymptote is if the degree of the numerator is equal to the degree of the denominator. So I'm going to just copy this and then change the word I want. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals a over b, and that's the ratio of the leading coefficients. And I'll write an example of that. So that would be something, maybe you got 3x squared plus 5x minus 7 over 4x squared minus 2x plus 13. This one would have a horizontal asymptote at 3/4. Y equals 3/4. Leading coefficients 3 and 4 out of that. Okay. Those are not random polynomials. They don't factor, is the reason I'm using those as examples. Because if they factored, we'd have to do a whole lot more work than just look at it like that. So I pick ones that don't factor. So ratio of the leading coefficients if the degrees are the same. So horizontal asymptotes are y equals 0 if the top is smaller, and the ratio of the leading coefficients if they're the same. That's the only times that horizontal asymptotes show up. Okay, those two rules. You've got to know those two rules as to when horizontal asymptotes show up. Okay. The next type of asymptote is the oblique asymptote. And you may hear me call it a slant asymptote. When I learned these, they just use the word slant. So I tend to gravitate toward that because that's the way I learned it. But oblique and slant are the same thing. So if you Google this and it comes up and somebody starts calling it a slant asymptote, it's the same thing. Obliques and slants are the same. Oblique asymptotes, they have a rule for when they show up. Well, we did if the top is smaller, if they're the same. Well, the next one is if the degree of the numerator is 1 more than the degree of the denominator. All right, so obviously need to do this. If the degree of the numerator is 1 more then the degree of the denominator, the oblique asymptote, and we'll abbreviate that OA, is the equation y equals mx plus b, because that would create a slanted line, right? Y equals mx plus b, slope-intercept form. The equation y equals mx plus b obtained by doing long division of the polynomials. Remember, we did this back before we were talking about, we did synthetic division most of the time. Sometimes you can use synthetic division. Most of the time with rational functions, that denominator is not a small one. So a lot of times you've got to do long division. We'll do some of those, but that's for obliques. And I'll write an example of that. If you had like x cubed plus 27 over x squared plus 9, if that was your function, that has a degree of 3 on the top and a degree of 2 on the bottom. So that one more than the bottom, so that creates an oblique asymptote occurs when that happens. Okay, so horizontal asymptote when the degree of the top is smaller by any amount than the degree of the bottom. So you got squared over the fourth, it's still y equals 0. If you got squared over the third, it's still y equals 0. If you've got squared over squared, it's the ratio of the leading coefficients. If you got cubed over cubed, ratio of the leading coefficients. If the top is one more than the bottom, so cubed over squared, fourth over third, squared over linear, that gets us an oblique asymptote, and we've got to find that using long division. So we'll kind of review long division as we go through this out of that. So with these asymptotes, one of the key things that kind of helps make it a little more horizontal and obliques never occur together. Horizontals and obliques never occur together, ever. The rules are different for them to exist, right? So they can't, none of the rules overlap. Okay, so horizontal, if you've got a horizontal asymptote, you don't have to look for an oblique asymptote. If you got an oblique asymptote, you shouldn't be looking for horizontal asymptotes. They don't occur together in rational functions. Okay, horizontals and obliques do not have to exist. You don't have to have those. Okay. Horizontals and obliques don't have. In most of the ones we're going to encounter in our practice here, they are, but they don't have to. You could just have vertical asymptotes and no horizontals and no obliques. That happens. But you will, if it's a rational function, you're going to have vertical asymptotes. Okay. The other two have to meet the criteria for those things. Okay. So we're going to work on asymptotes first, and then we'll add in the intercepts and a couple of other things that occur with rational functions. Okay, so let's start with an example. F of x is equal to x squared plus 7x plus 12 over 4x squared minus 1. Okay, so let's find the domain and any asymptotes. You can do that today before then. believe we'll be on good pace for what we're going to do. All right, so to find the domain, what do I do? Yeah, set the denominator equal to 0. So 4x squared minus 1 is equal to 0. I know that I can solve that by square roots because it's just got an x squared in it, but I'm going to try not to do it that way because I want to use that factoring later on. Okay, so I'm going to try to do that by factoring instead of using quadratic formula or square roots because that factoring is going to help me later. Okay, so how does 4x squared minus 1 factor? Nope. What's the method? Two terms with a minus sign in between. It's a difference of squares. 2x. Yeah, 2x plus 1, 2x minus 1. Doesn't matter what order you write that in. One's plus, one's minus. Okay? Then we can set those equal to 0. We get x is not negative 1/2. X is not positive 1/2. So our domain, all x's as long as x does not equal plus or minus 1/2. Same solution that I would get if I solved it by square roots, but where it's going to help me is I can take this factoring up here and check to see if this problem will simplify in any way. Numerator, how does it factor? Multiply to B12, add to B7. Yeah, x plus 3, x plus 4. Does anything cancel out? Do I have any matching factors? No. No. To be a matching factor, you have to be exactly the same. So you'd have to, if you're going to cancel out an x plus 3 on the top, you would have to have an x plus 3 in the bottom. Okay, so simplifying rationals, you've got to have complete matching factors. If something is tied together with addition and subtraction, you can't cancel just part of it. So like this x can't cancel that x with the 2x plus 1. It's got to be the whole factor out of that. Okay. So nothing cancels on this one. So what that tells me is that my vertical asymptotes are going to be the same things that I got here. I've got two vertical asymptotes for this particular rational function. So the VAs, the vertical asymptotes, are at x equals positive 1/2 and x equals negative 1/2. I have two of them because nothing canceled out. If one of the factors canceled out, then the vertical asymptote that exists is the only factor that's left. And we'll see one later on that something cancels out with. So we can see that happening. Now, the next thing to look at is the horizontal or oblique asymptotes. So we think about our rules about the degree. What's the degree of the numerator? 2. Degree of the denominator? They're equal. So that tells me I have what kind of asymptote? Horizontal at what? At the ratio of the leading coefficients would be 1/4. So we have a horizontal asymptote at y equals 1/4. The oblique asymptotes, because we had a horizontal, what do we know about the obliques? There's not one. There are none. Okay. Quiz and test, I might ask you what's the oblique asymptote, and one of the option answers might be none because there isn't one for that. And so you got to be aware, okay, if there is a horizontal one, there can't be an oblique one. If there's an oblique one, there can't be a horizontal one. It's okay if you don't have either of those, but you can't have a horizontal and an oblique happening together. Okay, so we have taken that polynomial on the top and the bottom and factored it, tried to see if something would cancel. If nothing cancels, then I just start referring back to the original. If something cancels, then I've got a smaller fraction to deal with, and I use that one from then on. Okay, because nothing canceled, I went back to the original and thought about degree. I can still think about degree here, but it's easier when it's a big polynomial like that to think, okay, just look for the biggest exponent. So it's a lot easier to do if you go back to the original if nothing cancels. Okay, so one down. Let's go, let's try another one. One does a little bit more stuff. Let's say we had g of x squared plus 7x plus 10 over x cubed minus 25x. So the first thing that we should look for this problem is what? The domain. Always going to do that before you simplify. You're going to have to do some factoring anyway to simplify it. So we're going to try to use that to help us find the domain. So for the domain, what do we do? I got an x. What's that leave in the parentheses? Yeah, and then that will factor as, yeah, that's another difference of squares. So we have three factors in our denominator. So that means we have three things that equal 0. So we got x equals 0, x plus 5 equals 0, x minus 5 equals 0. This tells us x can't be negative 5. This tells us that x can't be positive 5. So our domain are all x's as long as x does not equal plus or minus 5 and 0. And I'm just writing in set notation. That's fine with me for this stuff. There's a lot more stuff going on. So if you want to go to interval notation, you can, but set notation is absolutely fine for this. We're doing quite a bit of stuff. Okay. So we have three restrictions on our domain, positive and negative 5 and 0. That factoring is helpful when I go to simplify my fraction. So I have x plus 5, x minus 5, and then the numerator is a trinomial with three terms, so I'm going to factor it with the x method. Multiply to be 10 and add to be 7, be 5 and 2, so that'd be x plus 5, x plus 2. And now this one has a matching factor on top and bottom, so that's where our cancellation can happen, okay? So these two cancel each other out. So now the simplified version has x plus 2 on the top and then x minus 5 on the bottom. What that does for us is it changes our vertical asymptotes. Instead of having 3 vertical asymptotes, because we had 3 things in the domain restrictions, we're only going to have 2, because how many factors are left in the simplified version? 2. Those 2 are going to be your vertical asymptotes. You're going to have a vertical asymptote at x equals 0 and a vertical asymptote at x equals positive 5. So this is the mechanics of what's happening there. You're actually just setting that simplified denominator equal to 0. That's where that's happening. You've already done all that work over here when you found the domain. So it's repeating something. So I always just skip that showing that work. But that's what's happening. We're setting x equal to 0 and x minus 5 equal to 0. And that gets us the 2 vertical asymptotes. Chris?
Basically, whenever you find the domain, the numbers that you get whenever you enter the domain are the numbers that can't be in the domain.
Right.
And then, but those numbers are the vertical
asymptotes. That's right. Those numbers that are, like what he said there, was the numbers you find when you find the domain, or x's can't be that. When you find vertical asymptotes, they're going to match and have the same numbers as there were restrictions there, but you may have less of them. Because we had the canceling factor here, we had less of them. We didn't have the negative 5 as one of our vertical asymptotes. We'll look at the graph with the graphing calculator for this one in just a minute. Oh, there's plenty of seats up here front. All right, so vertical asymptotes should look a lot like your domain. Won't always match it completely, but can, okay? So we get vertical asymptotes. Notice that on the domain, it's not equal to signs, and on the vertical asymptotes, it's equal to signs, okay? And I'll show you this on the graph in just a minute. We're going to go ahead and find the obliques or horizontals, which whenever exists for this, if they do. So we can look. Here's the great thing about these is you can look at the original or you can look at the simplified, and you'll get the same answers for oblique and horizontal as far as which one exists. Okay, look at the original. What's the degree of the top?
2.
2. Degree of the bottom is 3. So the top is smaller than the bottom. Doesn't matter by how much, just it's smaller. That means we have a horizontal asymptote at what? Y equals 0. So, and if you look at the numerator of the simplified fraction, the degree of that is 1, right? What's the degree of the denominator? 2. Still, the top is still smaller than the bottom. Same result, same horizontal asymptote at y equals 0, but you get the same answer no matter which one you look at, if you look at the original or the simplified version. The simplified version is just a smaller problem, but it has the same characteristics as the original. Okay, that's what I want you to catch out of that. So horizontal asymptote at y equals 0. So what's that tell us about obliques? We don't have any. All right. Let's look at this one on the graph so that you can kind of see some of this stuff actually showing up and getting going. There it comes. When you're typing in these functions, you got to be careful to put parentheses around the top and the bottom in order to get it to graph correctly. Get mine to open up here. There it goes. So numerator, if I type in the original, x squared plus 7x plus 10, and I put it in parentheses, and then I do a division symbol, and then parentheses, and I'm going to type in the bottom, x to the third, minus 25x. Close the parentheses, and I hit graph. We see some stuff, weird looking graph coming up. It's got sections. It's got 3 sections of it. That's because it's separated by how many asymptotes. We got 2 vertical asymptotes, right? So that would cut something. If you cut a candy bar twice, it cuts it into 3 places, right? Same thing here. If you take a vertical asymptote, it cuts the graph into 3 separate pieces. This piece, the resolution kind of hurts us here, but this line keeps going up. There is a vertical asymptote at x equals 0 right there. We wrote one down, right? That it was x equals 0. Right here, what's that number? 1, 2, 3, 4, 5. We had a vertical asymptote at 5, right? So right here we see this graph, how it's shaping the graph. That's what asymptotes do. They kind of squeeze the graph into a certain form out of that. The horizontal asymptote, where does it exist at? Y equals 0. We see right here, see how this is separated there? Now here's the kicker, and this is where section 5 comes in, is vertical asymptotes you'll never cross. You never cross those. It's pretty difficult to run through a wall, right? That's a tough thing to do. That's kind of like the vertical asymptote. Okay, is a very sturdy concrete wall. It's tough to get through. Okay, steel reinforcements, that sort of thing. I've heard a lot about walls lately in the world. But anyway, horizontal asymptote is not quite as restrictive. You can cross horizontal asymptotes. You can cross oblique asymptotes. They're a little softer. Okay, so they're like a sheetrock wall or a plate glass window. You can throw someone through it if you're strong. Okay. No, they didn't say they died. They had a few stitches, but they died. But notice how this line, it's lying right on top of y equals 0, so we know that there's some x and y values that are y equals 0. Horizontal asymptotes you can cross. Oblique asymptotes you can cross. Vertical asymptotes you won't cross. Okay, so the graph, it's shaped by those things, but vertical asymptotes the graph won't cross. Horizontal and obliques it could. Doesn't mean it will, but it could. And when we get into the section 5 stuff, we'll start working on proving whether or not it crosses that horizontal or oblique asymptote. We'll work on that. Okay, so we can see those things that we found algebraically showing up when we graph it. That's what I want you to connect here, is the graph should show you the things that you find. If it doesn't, then maybe the things you found were maybe wrong, or maybe you typed in the graph wrong. Okay, Joe?
So the only difference between this and like parabolas is this is a fraction, and that's why it does the asymptote.
Yes, absolutely, absolutely. That's exactly the same thing. All the blue lines represent ordered pairs, just like they would with a parabola. The difference is we don't have a vertex because it's not a parabola. We don't have a axis of symmetry. We have asymptotes that shape it. That's exactly right. It's a graph, just like the first ones that you graphed in 7th grade with you pick some x values and you found y values and you start putting dots, and then we said, okay, now connect the dots. It's the same idea. It's just we've got a fraction and it does some fancier stuff. So as you get higher up in this, how many people did this in Algebra 2? Did rationals? People that had me should be raising your hand. We did some of this. We didn't do all the asymptotes and things, but we did some of the things with rational equations and things. So anyway, let's look at another one here and get a little bit of practice with what's happening with this particular function. F of x is equal to x cubed plus 8 over x squared plus 6x plus 8. All right, we're going to do the same things. We're going to find the domain, vertical asymptotes, horizontal, or oblique asymptotes, if those exist. Okay. So first step, domain. So we're going to take what? Denominator set equals 0. So domain, we're taking x squared plus 6x plus 8 equal to 0. And then solve it. If you're only asked to do the domain, you're welcome to use quadratic formula if you want to, but we know we're doing more stuff than that, so we're going to use factoring if at all possible. So we got a trinomial. What method we're using to factor it, Coach Kaufman?
The factoring method.
Say X. X method. Yeah, good job. So 8, multiply to be 8, add to be 6, Coach.
So
I need two.
Class, what is it?
No, I need two numbers that multiply to be 8 and add to be 6.
I have to think about that. Man.
This is easier than making out a lineup for a baseball.
Oh, well, I don't know about that.
I know it was always easy to write my name at number 9. But
what was the question again?
numbers that multiply to be 8, but add to be 6. Think about your numbers that multiply to be 8.
2.
2 times 4 is 8. What's 2 plus 4?
6.
Great job. I knew you knew it. So we got 4 and 2. So then the factors for that are what? Y'all help him out. Good job.
Oh, what?
Good job, Coach. Trust the process, man. You get
What class is it?
college algebra.
Well, that's the problem. I still called out.
Well, you took it at Memphis.
True.
Back when it was Memphis State.
Yeah, but you are using a blue marker there, so that counts.
That counts. Thanks, Coach. All right, so solve those. X equals -4. Can't equal that. X equals -2. Can't equal that. So our domain, all x's as long as x does not equal -2 and -4. And I didn't write that in the right order. I'm going to write it numerically. -4 and -2. Sorry. You don't have to do that. My brain says I do. Coach Kaufman is my baseball coach. 3 years.
Wait, not even good.
My name was closer to the top of the line, not the bottom. So,
Who was better, you or Coach Mack?
huh?
Who was better, you or Coach Mack?
We were not in the same era of
That's not
baseball.
what I asked.
I don't know. He played college baseball. I did.
Did you play ball in college?
I don't know. I didn't. So. Didn't get any scholarship offers, if that's what you're asking. So, all right, so we got our domain. Now let's get our simplified version. Numerator, how does it factor? This is where the rubber meets the road. You got the denominator factored. What about the numerator? So cubed, x cubed plus 8, which is a what? Yes, it absolutely is a sum of cubes. 8 is what cubed? 2. So we have x cubed plus 2 cubed. So that means we have a short piece and a long piece. What's the short piece? X plus 2. Short piece is always the same. Short, same. Both start with this. The long piece is the one that has the minus sign in it. And you got to think, okay, what's left? I used one of the x's. It'd be x squared. And then minus 2x plus 4.
All right, and plus is plus minus plus.
Yes, that's right. That's right. He's got the pattern right. That a sum of cubes is plus minus plus on their signs of the factoring. The difference of cubes is minus plus plus on the signs out of that. If you don't remember how to factor a sum of cubes, learn to. It's important. Okay. So because look at what factor cancels out now. That x plus 2 cancels that x plus 2. So we get this simplified version of x squared minus 2x plus 4 over x plus 4. So that helps us get a much easier problem to look at in order to get horizontal or oblique asymptotes out of this. So degree of the numerator bigger than the denominator by how much? 1. If I look at the original, 3 over 2, 3 is 1 more. If I look at the simplified version, 2 over 1, still 1 more. Okay, so it's still the same result. Now, where does the simplified one become easier? When there's an oblique asymptote, because the division from a linear into a quadratic is much easier than quadratic into cubic. That's a lot easier to do. So that's where the simplified version is really going to help you there. So there is no horizontal asymptote on this one because the degree rule fits oblique asymptotes. And to get that oblique asymptote, we're going to do that division. So we're going to take x plus 4 and divide it into x squared minus 2x plus 4. Okay. I'm going to do long division. I'm also going to show that you can do this one with synthetic division because we're dividing by what kind of polynomial? A linear one. So you could do this with synthetic division as well because you're dividing by a linear piece. Okay. Long division though, what times x gives me x squared? X. So I'll put an x up top, distribute x squared plus 4x and subtract. That'd be negative 6x. Drop the 4 down. What times x gives me negative 6? X. Negative 6. Subtract 28. The part that matters is this part. Our oblique asymptote is at y equals x minus 6. This 28 here, that's the remainder. It really doesn't matter. Okay. Once you get an mx plus b up here, when you do that division, you don't have to do anything else. If it's a larger problem, there may be other steps that could be done as far as the long division goes, but you don't have to do them because you just need the mx plus b because that's the oblique asymptote. If you did this with synthetic division, put a negative 4 up there, 1, negative 2, 4, up the 1. And this gives us y equals 1x minus 6. Same answer, doing it with synthetic. The only reason we can do synthetic there is because we're dividing by a linear piece. If it's quadratic or bigger on the denominator, you're going to have to do long division. So you've got to be able to do some long division there for that to happen. Now, what does that look like on a graph? So let's look at one that has an oblique asymptote on the graph. So parentheses, I'm just going to go to the original, x to the third plus 8 parentheses x squared plus 6x plus 8. We see this graph, kind of starts out looking a little bit like a quadratic, right? And then over here, it does this weird thing. Well, I'm going to graph that oblique on here. So the red line you're going to see is the x minus 6. It's that oblique asymptote. Look how that graph is starting to lean toward that. That this asymptote here is shaping the graph. There's also a vertical asymptote at where? At -4, right? So over here at -4 is right there. If we zoom out, we're going to see that graph getting more and more vertical as it gets closer to -4. Right, if we were to zoom out, and I'll do that. Let's zoom out. That was part of the domain. So that's where it's what exists is a hole in the graph, and we'll talk about that tomorrow. We'll talk about holes and intercepts tomorrow out of that. But here we see, and it also has another piece here out of that too. That's down here. When I zoomed out, I could see that. When I was at the 10 by 10 window, you couldn't see this part. It was down below. But we see this is our oblique asymptote. We see how this graph is shaped by that, just like it was the vertical asymptotes and the horizontal before out of that, right? And here we see this vertical asymptote here at x equals -4 that we see that's shaped by that. So that's what that graph looks like with that oblique asymptote happening. Okay. Tomorrow we will. We're just going to stop here. It's a good stopping spot.